Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Okay, the significance of the activation energy QS, which is normally derived as 38 Tm, right? How do we understand this? The plot of ln ds versus Tm by T, that is homologous temperature, shows that constant QS, okay, which is again, okay, this plot shows this QS is constant. So there is some typo here, where Tm is approximately is equal to 16.5 delta Hm, where delta Hm is the latent heat of melting according to Hasan. Okay, and delta Hm is actually the energy required to pull atoms apart to form the more open liquid structure, and it can have wide ranging values depending on cohesion. The melting point Tm and hence delta Hm increase with the degree of cohesion and cohesive strength. Okay, but the entropy of fusion, which is delta H by T, which is not sensitive to these differences, is essentially a constant for most metals and lies in the range of 2 to 5 calories per moles per Kelvin. So we are now trying to justify how we relate this activation energy to this value, and it has got some thermodynamic basis. So Richard's rule in thermodynamics puts this ratio to be around 2 calories per Kelvin per mole, and if we pick a value of about 2.3 calories per mole per Kelvin for common metals, we get QS is equal to 38 Tm. So this is the basis of getting this QS based on this thermodynamic consideration. Just to give an idea how we get the activation energy for self-diffusion in a pure metals. So now we look at the creep curve. We have already seen that, but then there are other perspectives. Several authors have described this creep curve in a different way. We will look at once again what is that. So this is a creep curve showing 3 steps of creep that we have already seen. Curve A is a constant load and curve B is a constant stress test. So Andreday's analysis of competing processes which determine the creep curve. So Andreday has analyzed the creep curve under the constant stress, which is this, and he decomposed into 3 curves. One is a sudden strain, that is instantaneous strain, plus the transient region, that is where the creep rate suddenly decreases and then reaches the steady state, plus a constant constant rate viscous creep. Okay, and then he just gave an empirical equation for the creep strain, which is equal to epsilon is equal to epsilon naught times 1 plus beta t to the power 1 by 3 into e to the power kt, where epsilon naught is instantaneous strain and beta and k are the constants. Okay, so this equation, if you put k, which is increment per unit length for a constant strain, constant rate, it will, if it becomes 0, then the transient creep will be exhibited by beta. Okay, so that is one way of looking at it. Yeah, some other people have improved this equation, and then what they have shown is a similar decomposition of the creep curve into instantaneous strain and transient creep and viscous creep, and then this is a total creep strain, which is given by this equation. Okay, so this particular equation is called exponential creep, and this term epsilon tr means epsilon true times 1 minus e to the power minus qt is called a transient creep term. Okay, and where q is the ratio between the strain rate to the creep strain. Okay, and this is a steady state creep strain. And then if you put together, then you see this instantaneous strain plus a transient creep strain plus steady state components. Okay, so this particular equation is proposed by Garofalo has unified all the above equations by superposing them into a single equation amenable to computer curve fitting methods. So by putting this kind of an equation, people are able to compare for how many materials follow this kind of an empirical equation during creep. So creep is, as I just mentioned, is a strong function of stress, temperature, strain rate, and these are primary. But then you have whole other structural features which are going to influence this. So each particular combination of stress, strain rate, temperature will drive each material class into different segments. So that is why all this, the individual steps which are shown here, they were all actually shown by some of the materials at some particular stress temperature combinations. Okay, it is nothing is general here. So people try to get a unified approach, whether we can create one empirical equation which is suitable for most of the material. That was the attempt, right? So that is how these all kind of equations are developed. But then only not that every material is going to follow, but then these kind of empirical relations gives us an idea what are the critical parameters which governs this creep deformation, and that's one advantage when you have this quantitative data, though it is semi-empirical or empirical in nature. Okay, now we'll move on to some phenomenological description of creep. Okay, so creep is being looked at by several researchers in a very different angle. So this is one phenomenological description which shows like this. What is this? This plot is again strain versus time only. But what is shown here is one is time independent curve and time dependent curve. So the difference between time independent curve, that is time independent curve, is A, and the time dependent curve. So you can see that this is a time dependent. As the time increases, you can also see that strain increases. And in this curve, as the time increases, nothing happens to the strain. So it is time independent curve. The strain is plotted for a constant stress applied at t is equal to 0 and held until the time t1 at which it is removed. So after the time t1 is reached, the load is removed. Then what happens? Then obviously we will be able to recover some strain. Okay, so that is called elastic strain. That is why it is called epsilon E, recoverable elastic strain, time dependent elastic recoverable strain. That is how you should understand this. Okay, because even in tensile deformation we are looking at the recoverable strain, but that may not be kept for so long time as in the creep tests, right? So this is very important. So similarly, you have the recoverable elastic strain and then non-recoverable plastic strain. For A, the initial plastic plus elastic strain is the only strain suffered by the material, and the elastic strain is recovered on unloading. In B, the strain increases with time. Okay, so this is one difference. So here we are not talking about the strain is only the elastic plus plastic is shown here, but here it is not. Beyond that, it is not possible. They are all pure plastic strain, right? On unloading, only the initial elastic strain is recovered and the initial time dependent and time independent plastic strains are not. So this is very important point. That's why the whole plot is brought here. The initial time independent and the time dependent time independent strain is brought back, and then time dependent plastic strains are not recoverable. So time dependent elastic strain, something you can recover, and time dependent plastic strain cannot be recovered. That's the idea. So a little more insights to this creep curve. Like I said that several researchers have looked at several aspects of the deformation and their influence and implications on the material behavior. In stage 1, which is also called a transient creep, strain rate decreases with time and strain. The dislocation density increases because of the work hardening, and in many materials, the dislocation subgrain structure is formed with a cell size that decreases with strain. So as the strain increases as a function of time, people have observed that the cell size also decreases. This is one observation. These structural changes are consistent with a decreasing creep rate during stage 1 creep. So now people are trying to understand what are the microstructural changes accompanying each stage of the creep curve. During stage 2, similar observations show that a steady state microstructure obtains, and this is consistent with the constant creep rate characteristic of steady state creep. So the stage 2 is a constant creep rate characteristics. That is what it is exhibiting, and it also should have a typical microstructure, right? What is the typical microstructure? The invariant microstructure is indicative that the recovery effects are concurrent with the deformation during stage 2. So I just mentioned in the beginning, any material which shows a steady state deformation behavior like this, there could be two competing events that takes place. In this case, work hardening as well as work softening, right? So work hardening will multiply the dislocation and the recovery will annihilate them. So these two rates, two reactions occurs with the same rate. So then the steady state is reached, and then the resultant microstructure is invariant microstructure. So that is very important, right? So only when the microstructure remains invariant, then your creep deformation will not affect the material's life. So these are the two interesting plots to understand the influence of temperature and the stress on the creep strain. So this is a strain versus time plot again, and what you see is with the increasing the stress and temperature, you can also see that the strain keep on increasing. Okay. On the other hand, the creep rate versus time also shows a similar trend. With increasing sigma and temperature, your creep rate also becoming very high. Okay. But you can see that the overall time to break is reduced as the temperature and stress is increasing. Okay. So this is what just I described here. So increasing stress and temperature raises the overall level of creep curve and also results in higher creep rate. So the overall increases this. The whole curve is shifted here. That's what it means. And then the rate also get higher. Stage 2 creep can be viewed as a region in which the work hardening capacity of the material is balanced by recovery or softening effects, I just mentioned. On a microscopic level, a steady state structure is also consistent with the view that non-conservative dislocation motion renders obstacles to glide less effective at elevated temperatures. And also with the notion that dislocations can be removed from the material by recovery. So it is, what is it we are trying to say here? We are talking about a steady state microstructure. Please understand that. So it has to be a non-conservative dislocation motion renders obstacle to glide less effective. So though the dislocation is moving, at any direction, that's why it's called non-conservative motion. It is not moving in any particular glide plane or any particular slip location. A non-conservative means it can move anywhere, even though it moves, but it provides, motion renders obstacles to glide less effective. So the obstacle to that kind of a motion is less effective at elevated temperature. This is the point you have to understand. Then only that kind of a steady state can be maintained. If you remember that, okay, if all the dislocations are obstructed irrespective of the temperature, then the steady state cannot reach, right? So that is the point. At the same time, the dislocation can be removed from the material by recovery. So whatever the dislocation generated is also getting removed by recovery. So during tertiary creep, the creep rate exceeds that of stage 2 and also increases continuously. This shows, sorry, there is a typo here. This is shown in a plot of creep rate versus strain. At the time, we will show the figure, which also shows that stage 2 is characterized by constant creep rate. That's we have already seen in the previous slide. The accelerating creep deformation of stage 3 eventually leads to material fracture, as shown in the figure, and this is related to several factors. Such alterations include onset of recrystallization, coarsening of second phase particles, and formation of internal cracks and voids. This point I have already mentioned in the previous slide, so it's only a redundant information here. So what is important is to understand the steady state microstructure, what is happening and what makes it invariant microstructure. So that point you have to understand. Other than that, these are all we have already seen. So a materials engineering creep resistance is frequently characterized by one or both of the parameters, that is strain rate, that is here we are talking about a creep rate, epsilon dot 2, that means a creep rate at the steady state, and TF, time to fracture. These are the two parameters which are very useful in the engineering applications. However, scientific discussion of creep is couched almost solely in terms of epsilon dot 2, provided stage 2 creep constitutes a significant fraction of material's total creep strain. Please understand that what we are now trying to say here is we can talk about this, why this is important, because these creep constitute a significant fraction of material's total creep strain. So the total strain experienced by a material during complete creep deformation, the major portion of the strain, irrespective of stage 1, stage 2, and stage 3, and stage 2 only accommodates huge amount of strain. That's what it is. Okay, that is why this stage is important. Epsilon dot 2 and TF are inversely related. Please understand, these are all inversely related. In a practical sense, epsilon 2 dot and TF represent extreme design criteria. Okay, we'll try to understand. Then why do we study this? If these two parameters, that is important. For example, if a component is intended for a short time elevated temperature use, for example, a one-shot rocket engine component, creep deformation may be tolerable, but fracture is not. So that is why TF is important. Time to fracture, that parameter is important. Though it is not, going to give interesting creep deformation data, but that time to fracture is very important because the component like, one-shot rocket engine component, that means it's only used only one time. And the time to fracture is more important than the creep strain in this application. So that is why this parameter is also studied. In such a case, TF is an appropriate design parameter. It is not creep strain here. Here it is TF is the appropriate design parameter. On the other hand, many components are designed for high temperature operation of hundreds to thousands of hours. That is a jet engine turbine blade. Okay, this is again very important. The jet engine turbine blade is going to be in use for hours and hours together. They are going to keep on running. Okay, and in such cases we need a creep data, or in some cases many years a boiler tubing. So jet engine turbine blade is one example. The boiler tubing, they are all going to subject it to high temperature and strain and for a very long time, to many years, right? So these are all two classical examples which clearly brings out the importance of why the creep strain is important, or time to fracture study is important. In these situations, structural integrity as reflected in a low permanent strain is required, and epsilon 2 dot is a critical design parameter. For many materials, the steady state creep correlated to these variables by an equation of the form epsilon 2 dot is equal to A into sigma to the power m prime into exponential minus QC by RT. So this is a very, very basic equation. So you have to remember, this is the steady state creep equation. Whatever we are going to discuss quite a bit of creep deformation and their mechanisms. So this is the basis. All the equations will follow this format. Okay, because we are talking about a steady state creep, where A and M prime are material constants, QC is the creep activation energy. So now we have a background to understand QC. The initial slides we have just discussed about how QC is perceived and how it is discussed, right? So A and M prime are material constants. In general, the above equation can be applied only over a limited stress temperature range, as the constants A and M prime and QC can vary with the stress and temperature. You have to remember, in creep is a strong function of stress, temperature and strain rate. A combination of these parameters will suit for different materials at a different context. So this equation also will work for a limited stress and temperature range, and because the other constants can vary with the temperature and stress. Okay, there is something called stress rupture. So similar way we discussed in the creep, the stress rupture is also a very important deformation behavior at high temperatures. Like time to fracture, that parameter comes only from this stress rupture test. So we are talking about creep test and the stress rupture test. And we have already discussed why the stress rupture test is important, because there are applications where it is just a one-time use, and then the time to fracture is very important design parameter as compared to epsilon dot 2, that is a steady state creep rate parameter. Okay, a strong time dependence of the strength becomes important in different materials at different elevated temperatures, which is high temperature for one material will not be so high for another. Yeah. To compensate this, temperature often is expressed as homologous temperature. So now this explains why in all the creep literature, especially when we look at all the temperature dependence, we use something called homologous temperature. Okay, just we want to avoid the influence of melting point. Just avoid the influence of melting point and look at the temperature. Then you get the true effect of temperature. Because the high temperature for one material may not be so high for the other material. So homologous temperature is a normalized parameter to compare. The tests which are used to measure elevated temperature strength must be selected on the basis of time scale of the service which the material must withstand. So we just looked at few examples like a turbine blade in a jet engine and boiler tubes, and we looked at rocket, jet rocket components and so on. So the stress rupture data is plotted like this: stress versus rupture time. So you can see that not always you get a straight line like this for most of the test, and the basic information obtained from the stress rupture test is the time to cause failure at a given nominal stress for a constant temperature. The stress is plotted against the rupture time on a log scale. So you can see that a straight line will be usually be obtained for each test temperature. So it is for every temperature there is a straight line, but changes in the slope of the stress rupture line are due to structural changes occurring in the material. So you see that this is a simple straight line, but on the other hand, you have the change in slope takes place at 650, and then the change in slope takes place two times, one here and another here, 800. So the changes from the transgranular to intergranular temperature fracture, right? So this also we talked about when we talk about ECT temperature, right? Transgranular fracture to intergranular fracture. Yeah. So oxidation, recrystallization, and grain growth, or other structural changes such as ferroization, graphitization, or sigma phase formation, and so on. So all these things can. So this is also an indication of something happening into the material when you see the slope change in the stress versus rupture time data. So what is the primary difference between these two? We are talking about creep test and the rupture test. So I just tabulated just for some key features. In a creep test, we measure, it measures the dimensional changes which occur from the elevated temperature exposure. On the other hand, stress rupture test measures the effect of temperature on the long time load bearing characteristics. So this is very important. Creep test not necessarily up to failure, because we are only interested in steady state creep, which is the design parameter. But here the test is to failure normally involves very high loads and very high creep rates, right? Tertiary creep and all we will cross. And there is something called the minimum creep rate, MCR, which is a design parameter, which is normally defined as the stress to produce a creep rate of 1% per 10,000 hours, or 2.8 into 10 to the power minus 10 per second, or the stress for the creep rate of 1% per 100,000 hours, about 11.5 hours, or 2.8 into 10 to the power minus 11 per second. So this is how the minimum creep rate is defined, in this order. Okay. So the typical time taken for creep test is 2000 to 5000 hours, but here it is just around 1000 hours. This total strain is often less than 0.5% in the creep test, and here it is nearly 50%. So these are the primary difference between these two tests, creep test and the stress rupture test. But then the purpose of measuring these parameters are quite different, and which also we have discussed elaborately. Okay? So now we will just discuss the creep mechanisms based upon the stress, strain rate, temperature combinations. There are different interesting mechanisms possible, and it is not going to be the same mechanism for every material. We are going to talk about crystalline materials first, and then we will go to non-crystalline material and so on. Okay. So I will stop here today, and then we will continue in the next lecture. Thank you.